Hi, Michael. Welcome to the Materialize type class with Magnolia session. Thanks, for introducing me. And who am I? I'm Shameera Rathnayaka and senior engineer at Spotify, Slate, and Apache committer and open source enthusiastic. Um, so today's agenda is we gonna talk about like what is type classes is and what is why we need it, and then we are going to design a type class, and then there's a tiny library we are going to implement called JSONify. Then we talk about Magnolia, how we use it, and then talk about the converters that we are using in Spotify, and then some benchmark results. Yeah, the type classes. So what's it? What is it? In Wikipedia, it says like a type class is a type system construct that supports ad-hoc polymorphism. In the more simpler words, like it's a way that you can program a technique that let you add new behaviors to the class types without using inheritance and without having access to the original source code. Like if you have some files in some libraries, then you don't have access to those source, so you can actually without using inheritance, you can actually add some new behaviors. So that's from the advanced Scala with cats. So ad-hoc polymorphism. It's nice. It's a kind of nice word. So what is it? It is like method overloading for functional programmers. And like here we have a thread called show, and it has a method called show as in the definition, and then it returns a string. So the same like case class that we have here in person that actually extend show and override that show. So better example would be like if we have something to add up, like we can have like multiple way to like add two elements together. In either we can add it as an integer, either we can add it as a strings. So in that case, we can actually run like we can define this different adding methods for the same class without touching the source code, like the original source code, and give this different behavior based on the type classes. So this is that we call like ad-hoc polymorphism. In general, polymorphism, actually we like keep the behavior and the data in the same place, but with ad-hoc polymorphism, it gives us a way to like, we can decouple, like we can keep the data separately, and then we can keep the behavior separately out of that, like in a separate class. That's really like clean way of doing that. Here is an example that we try to use in like the people I use person class. So here person class is like just a case class, doesn't have any show method. But we have a show type class which extend like it's give a like a behavior, the show behavior to the person type case class, but the logic is in a separate place, not inside the person. Okay, designing a type class. So designing a type class, there's three different design roles here. Like when we are designing a type class, one is define pure abstract types with at least one generic parameter. Like we need to have at least one generic parameter, like type T. Show bracket T is like T is a generic parameter. We need at least one. We can have multiple. And then we need to implement this abstract type for the to create an instances that we need to support. For example, we need to support per person like type to support this show type class. Then we implement type show person. That's the implementation. We can actually if there's no any implementation, then we can't use that like behavior on that top of that the type. So that's we can limit the scope for this only supported type. And then we need to create an operation with like we need to create a method that which take this type class and then the object type, and then call this behavior on top of that type. So this is like, so how we define design this is Scala is like we can use the Scala built-in features like thread, case classes, and implicits, and then we can achieve this ad-hoc polymorphism, like design these type classes like out of these three rules. In the slides we have a show and the semi group. It is kind of combining two types and produce the same type. So we can actually use this like trait and like this is the type class is the one generic type parameter, which is P, both show and the semi group. So we can use like as I said, like trait classes is like and to design this type class. Let's talk about the JSONify. So JSONify is a tiny library that we want to implement, which convert the Scala class classes to JSON representation. So we have this the pre-given data, like we have a ADT, JSON ADT. So we have a couple of case classes implemented, like JSON string, the basic to cover the basic JSON types properties. So we have number, the Boolean cover, and array and object. So object especially like take name and then the map, which is properties of that object. All these types are JSON. And then we have a type class. So we have a JSONify type class with a type parameter T. And then it has a method to JSON, which take the value and then output this JSON type. And then we have the JSON printer, which is which has a print method, which take the type T and then the context bound JSONify, and then it convert the type T to the string, which is a JSON representation. So we have decoupled this logic, like how we convert the T to the JSON and then JSON to string. So for that we have another private method called print JSON, which takes the JSON object and then return the string. So once we know how to convert this T to the JSON type, and then we know how to convert that to the string representation. So design the type class. So we need to design type class for the JSONify. So first thing is we need to define it. So we have the trait and few abstract type with at least one parameter. So we have only one parameter here, and it has a to JSON which take T and then return JSON type. And then the implementation, in a JSONify object, we have this auxiliary constructor like spec function, which make it easier for have this multiple implicit reduce the code. So we have string JSONify, which take a string and then convert it to the JSON string, and we have JSONify integer. So which take the integer and then convert to the JSON number, and also the Boolean. So we can have whatever we support in types defined here. So we have the implementation. So operate. So as we see, JSON printer is our operator. It has a print method which take the type and the JSONify, and then do that or use that to produce some behavior. So short recap here. So what values JSON printer can print? It only can print the values that the implementation, the instances that we define in the JSONify object. But so that's only limited to those types. But what about the use-defined classes? If I want to use this JSONify library and then I have my own classes, so I need to JSONify my types. So how I can do that? Will this work? I have my address and person case classes implementation, and then I create a person and then I call the print. So this won't compile because it doesn't find the JSONify person. So either I have to define it here, or I need to get it from the JSONify object, which is not possible because that's a library, so it doesn't have user-defined types in implementation. So we have to define it by ourselves, right? We define the JSONify address and person because person has an address as one of parameter. Now we can call the JSON printer.print with the person, and it has all these context bound implicits. So can't we simplify this now? So it's a really cumbersome to define JSONify for all the custom type. If you have a bunch of custom types, you would use the case classes, and you have to provide the implementation of JSONify for all of these types. So how about we derive JSONify for any user-defined types? That sounds awesome. So how we can do it? There's a multiple ways to do it. First is we can use low-level macros. We manipulate a tree, and we in the compile time we get the type T, and then we generate some classes. So generate some classes and also justify construct. So it will be available to the scope. Then we have Shapeless, which is like another big library, which also can use to accomplish this. And also Magnolia, which is not broader, like it's just focused on like how to derive these type classes. The Shapeless is the deriving type class is one use case, like it covers a lot of the other use cases. So Magnolia is a really simple library that specific to the deriving the type classes. Let's talk about a bit about Magnolia. So in the Magnolia, the propensives, the documentation, it says like Magnolia is the generic macro which automatically derives some, materialize some type classes for a product and the coproduct types. So here we have the product and coproduct types. So the country is a coproduct, which is a trait have a multiple case objects. And then the address is a product type. It has some parameters, and one of these is country. So if it is support these both cases, then actually I can use it to like derive my justify for address, and same for the person as well. So and it supports recursive defined data type. So so it actually like when you have type the justify derive some justify type T, and then you encounter the down the chain like again same type, and it doesn't like derive again, like it use the like it's kind of use a caching mechanism, like it keep track of like what types it derive and then use it. And then if the derivation fails, the error message are detailed and informative. That's really awesome. That like if you're trying this new library and then it's everything is like in macro, it's really hard to like dig deep in Magnolia, which is like a wrapper for like high level wrapper, and underneath that like it use a lot of macro, like low level macro. So it's really hard to like debug if it doesn't support like use like nice where it fails and stuff like that. So it's good at the derivation fail like really easy. Like it's say like which type you can't like it couldn't like derive. So that's really awesome. So you can find the Magnolia in the GitHub propensive/Magnolia. It is open source, so you can use it. Okay, so in Magnolia, like let's dig deep, like how we can actually use Magnolia to like derive our JSONify object. So the basic construct here is the structure of this. The derivation is like this object, like this is this coordinate snippet. So first we import Magnolia, and then we enable the macros, because Magnolia working with the macros, and we are going to use the macros in this here as well. So the my derivation object has three things. One is the type constructor, and then the combine method, and then the dispatch method. And then we have implicit general method, which is actually called the macro. So we need to have this all type constructor, combine, and dispatch method in the same place, because in the compile time, Magnolia need to find these things. So we should like put them in the same place in the object. And so let's use Magnolia for our JSONify. So type constructor. So what our type constructor is JSONify T. So we define it, and then we have combine. So the first block is like a person block, a person case class, and then so we need to derive the JSONify for the person. To do that, we need to implement the combine method in the Magnolia derivations. So here, if you see like for a given type T, I get a like case class object from the Magnolia, and then I need to return a type class T, which is the type we coded our type construct, which is JSONify T. So I'm creating a new JSONify and overriding the to JSON and get the value T, and then I put in JSON type. So the important thing is like how we do what we are doing in this to JSON body. So first we access the parameters of the passing case class, and then for each case class and for each parameter we create a map, because what we're trying to do is like we try to convert this the case class to a JSON object, which take the case class name and then the properties, the parameters, property map. So we constructing that with the for each parameter we get the name. Label is the name of the parameter, and then each parameter the as you can see in the third block, we have the like structure of the case class, the Magnolia case class, which if I walk through like this example, like when I'm getting a case class in the second block in the combine, what we are having is like the case class with the type class T, which is we define type construct, JSONify T, and then the type is the person type. So, and it has some properties like type name, which is the, you have the package name and then the type name as a type term. And then the sequence of parameter list, and these are the like parameters that you need to like construct the case class. So we accessing that parameter list, and then we convert that to the name, parameter name, and the JSON type for each parameter. And in the parameter trait, like if you see the parameter itself has like a type class for each type parameter, like parameter type. For example, for the first type, in the person is a name, is the string, is the parameter. So we will have JSONify, and then the type is string in the fourth block I'm referring here. So the type P type would be the string, and then the P label would be like name, but that's the name of the parameter, and then the type class is the type class of that the JSONify string. And then the dereference is like when you pass an instance of the case class, and then it returns the value of that parameter. So we are using that in our third second block in the combine method. You can see here. So we are using the case class parameter, and then we are labeling type class and show and construct the property and then the return. And you can see like for the address, we get the address and then the show method in the fourth block, and then we get the address. And address itself, like we define like the same thing, same pattern, same thing going through like then Magnolia derive the type class for the address case class as well. Cool. And derive type class for product. So I get it like it's I take it to the different slide, like that's only dispatch method, like it has a lot of code. So dispatch is like handle like where the Magnolia handle the coproducts. So we have the country seal trade, and it has different implementation, US and Sweden. So 100 code. So we only support those two countries. So we can implement so JSONify for the country. So we are limiting that. No one can actually implement any JSONify for different countries. Like this is like we are scoping the countries to US and Sweden. And we here dispatch. What we get is like seal trade. Like it's a seal trade that's kind of represent the country. And you can see that in the third block, like the seal trade is like take two type parameters. Type class, it's and with the types, and then the actual type. If you check the like the interesting point here as also is like two JSON body. So how we derive the JSON type from the what we have with the seal trade. So here we have seal trade.dispatch value. We have to pass the value, that the object that we are working on, and then it return off the subtype object. So if the subtype, we will like, so we pass the country, then it return like which country subtypes we have right now. And then, and we cast that to that type, we cast the value to that type, and then we get the to string. So this is simply like how we convert the seal trade object case object to like this JSON string. So interesting to know like how this data is working, like the seal trade. The type name would be like the same one, like same thing. We have the object, the package object, and in the country, the type, and then each dispatch method. You can see we pass the actual type, and then we have a different return types. So we need to pass this handle and the second parameter list, and it has a subtypes and data type. So we are using this to like construct the body of the JSON to JSON. So it's more recap here again in the JSONify. So now we have all these things, like we have the type constructor defined, and we have the combine defined, and then we have the dispatch defined, and we put the implicit generator here, and we have some primitive implicits that we are going to support, like string, boolean, and those stuff. So that's our primitive implicit. We have to provide those things, like that's like Magnolia is like only working like case class and trait level. So we have to provide other implicit, like for the primitives. And we have auxiliary class, like simplify that. Okay, it's time to draw some type classes. So it's really easy. Like, so we have the test JSONify method, which as a main method, and it imports the JSONify. So like this is how we bring the derived classes, like the Magnolia derivations within scope. And then we construct the person object, and then we just call the JSON print for p, and this will work. Like this will output the JSON representation of the like string representation of the JSON, and it won't output the pretty print. Well, this so we don't have implementation of pretty print here, but you can assume that that's pretty print our JSON. So basically, this JSON is like kind of a string, the output of the JSON print or the print p, and it finds the JSONify because JSONify is derived from Magnolia. So we don't need to define that. We don't need to get it that we don't need to define person or either address. So and also for the country. So everything is derived, and I'm a pretty happy use of this tiny library. Like I don't have to define any of my JSONify for any of my custom types. It automatically derived. That's really awesome. So when we are using Magnolia, there are some things we should notice. Like we should like know that Magnolia doesn't support more than one type parameter. Like for example, if you have kind of encoder which takes the type t and then convert it to the type r, and we have method encode, and it doesn't support like natively. It doesn't support, but we have some workaround. Like for what we can do is like we construct the type class for encode and for the type for all the type t, and we need to define the R type for all the JSON types. We have an encoder. So this is like we are converting the to multiple type parameter type class to like one type parameter one type parameter type class. So we have to define this encode like the Magnolia derivation for encoding a different for the different types. One for JSON and one for something like we want to convert. And another thing is like implementation heavily depend on the type class variable. So so first one, the JSONify is like a contravariant type class. So it takes a type t and then output the string. It's a fixed, so it doesn't depending on the t. And then the covariant types is like you output the t. So you have to construct that t inside that method. So you have to really get familiar with the Magnolia APIs, the the case class or seal traits. So you can construct, pass in the required parameters to the constructor method to like construct your type. It's pretty. It's a bit harder than the contravariant thing, like where you get the type and you produce something. But it's doable. So the interesting, like where we use Magnolia in Spotify. So we use in Scio, which is Idiomatic Scala wrapper for Apache B. So we use that for coded derivation. So we, if you have family with Apache, then you have to define coder for each input and output types. So it's a really cumbersome. Like if you want to write the coder for every custom type that you are using, so we provided us like. If you want to provide us, that's fine. So if there's no coder find in the scope, then we will derive for you. And then we use for testing, so generate materialize some type classes. And then we have the Spotify magnolify, which is a nice add-on collection of add-ons to common type class derivations. If we are using Scala checks for testing,
And we have property-based testing with deterministic generator, like we generate the deterministic gens for Scala checks using the Magnolia, and arbitrary types derivations. And then derive, the magnolify has all the type classes derivations, and some data converters that we heavily we are using in the Spotify, such as Bigquery, Avro, and Bigtable. Let's talk about the converters. It's really interesting. So deriving case classes for common serialization format, like, so when we have a converter, we have the type T, and then we have a reader and a writer. So this is like we are working with the multiple type parameters, and this is, we have converters for all the data types: Bigquery, Avro, Bigtable, data store, and TensorFlow, and all stuff. Let's talk about like how we use an AvroType. So Avro, like Avro work with the generic records. Is basically like you have a put and get methods. So you put some key value is object types, and then you get object using that key, string key. And then so generic record has a default implementation which has the schema and then the list of objects. And the associated schema is look like this, like you have enum types, record enum, array map union, and then the field which has a string, schema, docs, and default values. And so we can use this CL tray to represent the primitive field. So we are using it like Avro field, which is we have two types from T and to T. That's depending on the like implementation. And we have schema. We have a bunch of methods that we need to use to work with Avro field, which is a type class. Now we have entire generic record. Like so we have the type class for each field, Avro field, and we have a type class for the entire generic record, AvroType, which is a converter with the type T, and it convert a read from generic record and it write to the generic record. It's like read generic record, construct T, and then write convert that to the generic record and write it. So that's it. Like that's why we have these two auxiliary constructors here. Get the generic record, return a T, and then get the T and return the generic record. Yeah. So and like for the Avro, the types that we read and write are not exactly the same every time. For some it's the same, like for integer it is the same, like the read values are like the what by Avro types are integers. We can map it to the 1-to-1 like integer in the Scala, and but not for all the cases, like for the string, like in Avro world, the string is kind of a char sequence. So char sequence, and when we are reading, we need to read from char sequence and then construct the string type. And then we're writing, we work with the string. So that's like it's a bit different, like what the read and the write types. So we have implementation, like auxiliary implementation for the types. And then we have the important, like here we have the like combining for AvroType. So we get the case class, and we need to provide like provide the Avro field. Like here we are like implementing the Avro field. So because Avro field is used by the AvroTypes. So here we have from T, we defining the types, and then we implementing this using the case class that we are receiving. So so in the from method, you can see we use a case class construct to construct the type T. And then the to method, we use parameters to actually construct the generic record from the T. So this is like the contravariant and the covariant, both example in one place. You can see like we use different APIs to like work with those. And we don't support dispatch right now with the type class AvroType. In future, we can work with the union and other types that need dispatch, like coproduct type support. Right now, we don't support it. In future, we might. So let's see how AvroType in action. Like so, if you are using, so we have AvroType like derivation in the Magnolia magnolify. So we import that into the scope, and then we create new case like our case classes, and then we create instances, and then we call the AvroType then foo, and it will derive the AvroType for us for this foo. And then we can use converter to convert from the type foo to the generic record, and then generic record back to the type foo. So here we are convert the generic record, and we are accessing this schema. And then the next like last we get the generic record, and we convert back to the foo. So we will get like one-to-one like machine like the same foo object back from the generic record. So its round trip should be equal, like foo instance convert to the generic record, and generic record back to foo should be equal. So we have other converters, other than the Avro. We have for the Bigquery, it convert from type T to table row, and we have Protobuf a converter, and we have TensorFlow converters in Magnolify, and we have data store converters, and a bunch of more other converters. For Guava we have, and Cats we have, we talk about it. So there are multiple Magnolia derivations for all these types. So let's talk about some benchmark. This is not officially the done benchmark. This is something that we ran in like in our computer, local computer. One of my colleagues ran this one, and I got that benchmark result from him. So we used to have shapeless in our the Scio and the libraries that we used before Magnolia. And so we replace that with the Magnolia, and then we see compile time the differences for arbitrary, and the converters is really big, like really fast in compile time compared to shapeless. And also we did some converter nanosecond operations. So it's also like Magnolia is pretty fast compared to shapeless implementation. So it's pretty fast, like, because I think that's the only reason is like it doesn't derive the same recursively, doesn't derive the same types again and again. So it's, and also some improvements, yeah, in the Magnolia code base. So you can find references here, Magnolia, Propensive, Magnolia. It's a really good documentation. If you go there, and you will see like really good instruction, like there's a tutorial, so you can follow and then use Magnolia. And if you want to like use Magnolify, it's available in Spotify GitHub repository. And then we have Scio, and there's a talk done by Neville and Claire in Scala 2020. You can access that. And thank you.